Welcome to section 410. Today is an exciting day because it's the gateway to integral calculus, which is what we're going to do all next semester, as opposed to this semester when we did differential calculus. So let's start with the definition. Big F is an antiderivative of little f if the derivative of big F is little f. And here are three examples of functions that are all antiderivatives of f of x equals 2x plus 3. Because the derivative of each one is 2x plus 3. And in fact, if I add on any constant, it will be an antiderivative. And so we have a name for the set of all antiderivatives of a function, and it's right here. It's the indefinite integral. So the notation is you have an integral sign, and then you have the function that you're integrating, and that's the integrand, and then a dx. So an integral sign always has a differential. They come in pairs. And that's equal to any antiderivative of little f plus a constant. So on the next page, I have a set of all the antiderivative formulas that you're going to need to know. And don't worry, most of them are just the opposite of differentiation formulas, so they make a lot of sense. And you'll see as we go through why they make sense. So the first one we're going to look at is the trig rule for cosine, which is the integral of cos kx is 1 over k sine kx plus c. So if we apply that formula over here to this function cos 2x, then we get 1/2 sine 2x plus c. Now the check is the derivative of 1/2 sine 2x plus c equal to the integrand? If it is, then we did it right. So let's take the derivative. The 1/2 is a constant, so it just sits there. When we take the derivative of sine 2x, we need to multiply by a 2 by the chain rule, and then cos 2x, and the derivative of a constant is 0. So the 2 cancels with the 1/2, and that's cos 2x. And so that's our integrand, and so indeed our integral was right. So again, integral signs always come with differentials. Don't leave the differential off. It's kind of like parentheses. You wouldn't go around writing a half a parenthesis. They always come in pairs. I think they always come in pairs. All right, so let's do a few more examples here. This first one, I'm going to use the power rule, which is right here. And I'm going to use the fact that constants like the 4 and the 2 behave just like they do with differentiation. So this integral is equal to, I'm going to put 4 there, and then I'm going to integrate x cubed using the power rule. So that would be 1/4 x to the 4th. And then minus 2, and I'm going to integrate x using the power rule, 1/2 x squared. And then I add on a constant. And then I do a cleanup, x to the 4th minus x squared plus c. Now you can certainly do this middle step in your head. I'm fine with that. I do it in my head. I would have, let me clean this integral up. I would have gone straight from this line down to this line. And let's just do a quick mental check. Take the derivative of x to the 4th minus x squared plus c, and we're going to get 4x cubed minus 2x, which is what we wanted. Notice also, once you integrate, you drop the integral sign and you drop the dx. So as soon as you find an antiderivative, which I did, this is the second line, I found an antiderivative, there's no more integral sign. So the next one, notice the differential is dt, integral of x cubed dt. That means the variable that we're integrating with respect to is t, not x. So actually x cubed is a constant. X cubed is a constant, and I can use the constant rule right here. So this gives me x cubed, which is the k in that rule, times t, because that's the variable, plus c. So that is the integral of x cubed dt. So the differential is very important. That's the point of this example. Now the last one, it just makes no sense. You can't have an integral sign without a differential. Okay, properties of indefinite integrals. Indefinite integrals behave the same way derivatives behave with respect to sums, differences, and constants. And so you're going to use those rules without even knowing them. I was using those rules right here when I found that antiderivative. Okay, basic integral Bible. Again, you need to memorize all these formulas, but most of them are just going to be intuitive. For example, this one here, the integral of e to the kx dx, a 1 over k comes out. And the reason for that is that when you take the derivative of e to the kx, a k comes down. And you want to cancel that k, and that's why the 1 over k is there. All right, let's do some examples. The first problem, find a general antiderivative for f of x, and this is f of x. Another easier way to say that is just find the integral of f of x dx. Now to do that, I'm going to use a couple of formulas from your Bible, the power rule and the constant rule. So let's go through that. This is equal to 2 is a constant, and then when you integrate x cubed, I get 1/4 x to the 4th. Then I add on 3, which is a constant, and the integral of x squared is 1/3 x cubed using the power rule. The integral of x is 1/2 x squared, and the integral of 7 is, by the constant rule, 7x. And that's because the derivative of 7x is 7. And then I add on a constant. Now, you can certainly do this step in your head, and I am fine with that. If we simplify this, we get 1/2 x to the 4th plus x cubed plus 1/2 x squared minus 7x plus c. And as you do more of these, you'll be able to do this intermediate step in your head. I'm just showing that so you can see how I get my final answer. Okay, the next one, we need to rewrite it before we can use the power rule. So I'm not going to integrate yet, which means I need to keep my integral sign and my dx. So this is negative 5x to the negative 3 plus 6x to the 1/2 dx. And now I can use the power rule. So this is equal, negative 5 is a constant, and then to integrate x to the negative 3, I get negative 1/2 x to the negative 2 using the power rule, and then 6 times, if I integrate x to the 1/2, I add 1 to the exponent, so I get 3/2, and 1/3 is 2/3. So pause the video, make sure you follow that, and then x to the 3/2, and then plus c. And let's just clean that up. That's 5/2 x to the negative 2 plus, this would be 4x to the 3/2 plus c. Okay, one more using two other formulas from your Bible, exponential rule, and I'm just going to call this the 1/x rule. It really has no name. So this is equal to, instead of bringing a 4 down like I would if I was taking the derivative of e to the 4x, I bring a 1/4 down. 1/4 e to the 4x, just leave the exponent alone. And then the integral of 1/x, we can't use the power rule on. That's ln of the absolute value of x plus c. And the reason you can't use the power rule on 1/x, come up here, 1/x is x to the negative 1. And so if you try to use the power rule for the integral, you'll add 1 to the exponent, you'll get 0. And so then up here, you'll have 1/0, which makes no sense. Okay, initial value problems. We're going to do one of these. These are just integration problems. You're given the derivative of a function right here, and you're given an initial condition right here. And your job is to find the function. And there's 3 steps, and I'm going to walk you through these steps with an example right here. And the steps up here, I'm using y as my function, but since this problem is using f, I'm just rewriting the steps with f instead of y. All right, step 1 is to find f. So f of x is equal to the integral of f prime, which is 6e to the negative 2x dx. I really want to see this step. And now we integrate. That's 6, and the integral of e to the negative 2x is negative 1/2 e to the negative 2x, and then we get a constant. And yes, you could certainly do the simplification in your head. That's just negative 3 e to the negative 2x plus c. All right, now we need to find c. So we're going to use the initial condition. So 1 is equal to f of ln3. But we can compute f of ln3 because we have f of x right here. So put ln3 in for x. Negative 3 e to the negative 2 ln3 plus c. Now we just solve for c. So 1 equals, this would be negative 3 e to the ln. I'm going to bring that negative 2 up as an exponent. 3 to the negative 2 is a 9th, plus c. Now, e to the ln 1/9 is 1/9. So we get 1 equals negative 3 times a 9th plus c, which is 1 equal negative 1/3 plus c. So now I'm running out of space. Over here, c is 1 plus a third, which would be 4/3. All right, we're not done. Step 3 is to put steps 1 and 2 together. We have f of x from step 1, but we don't know c. But now we know c from step 2, so we can rewrite f of x with no constant. F of x is negative 3 e to the negative 2x plus 4/3. And that's your final answer. When you solve an IVP, you get a function. Okay, and that's the end of this section.